Now, of course, this may not be the best example because for omega 2 is just a constant, so you can actually just shift everything. But what if this is not omega 2 is not just not the straight line? What if it actually has at an angle, maybe something like this? If like this, so it's going to look like this. Right? And the total motion is what? The total motion is the summation of omega 1 plus, let's call this guy omega 3. So this is omega 3 with the dashed line. So what's the sum? The sum is omega 1 plus omega 3, which is the superposition of these two. That's the total. However, keep in mind that this total is only true if you superimpose everything to the very end. At this point, if you sum it up together. And the problem is sometimes it's not that easy to calculate each one of them at every time. So some people say that I'm going to let the ball to experience this omega 1 first. So I calculate this value, and then I'm going to let this ball to experience omega 3 for this much time, and I put these two together. Add these two and then get the final value. Sure, that's one approach. But the order for this kind of superposition actually changes the way you find the final answer. The result is not going to be the same because the point will move from one point and then you shift it or you move this one and move to the other direction. That's not going to give you the same result. But Leonhard Euler found one thing, and he discovered that, yes, it's true for a long period of time, or from time to 0 to maybe after perhaps 5 minutes. That superposition actually is order dependent. So, but he realized that. He said, what if we don't look at the change of angular velocities or angular acceleration for a long period of time? What if it's just for that instant? Just for that instant, just for the moment, just take one moment. For the time moment here, it is true that the final position, which is the total summation of these two, it is the summation of these two, one by one. Right? So suppose this is the total. It is actually this plus this. And by saying that, we ignored the causalities beyond this point. We don't care how you add these two together, whether you add this one first or you add this one first. You add omega 3 first and after, or omega 1, or you add omega 1 first or then omega 3. What I said adding, that means either you spin the ball in this direction first, and then you spin it in the other direction. Which order you choose doesn't matter. Because Euler series says that I don't care what happens here. I don't care what happens after that. I only care about at this moment. At this moment, there's a linear relationship between omega 1 and omega 3, and that's it. So in that case, it doesn't matter which one you're choosing. So that's the keen observation made by Leonhard Euler, which enables us to calculate or analyze angular motion as well as general motion in three-dimensional problems. So the mathematical expression of Euler theory, it's very, very simple, but you have to understand the significance and the physical meaning, which is one I just described. So here, this is what he said. He said, suppose you have a structure in 3 dimensions. And suppose we can actually consider that there's a plate like this. And the plate, of course, we deal with the plate problem several times in XYZ like this. And the plate experiences angular motions in, let's say, 2 different directions. One is here, we call it omega 1, and another one is this, omega 2. Suppose the plate experiences omega 1 and omega 2. So according to Euler theory, and he said that the unit change at that particular instant, because omega 1 is going to lead to the angular change. For that time instant, you can call it d theta 1, because it's very, very tiny. That's why we saw d theta 1. For omega 2, it's going to cause the very small angular change. We call it d theta 2. So according to Euler theory, he said that the total angular change, of course, all of these must be in angular. That's why they are going to be written in vector form. So that's how you can put these two together. So what Euler says is d theta, the total angle, must be equal to d theta 1 plus d theta 2, only for that instant. And if this is true, you can also say that total angular rotation, the sum of these two equals to omega 1 plus omega 2. Now, what's the significance of this? The significance of this is that if this is true, now we can actually consider more interesting problems. Suppose we still have the plate. Define like this. And you can define a local coordinate system. And this local coordinate system, usually we like to choose the center of gravity, right? You know that finding the center of gravity is the key in understanding the angular motion or even general motion of any three-dimensional objects. So we're going to have a x, y, z, defining the local coordinates at the center of this three-dimensional plate. And for civil and mechanical engineers, we also care about the motion of any object with respect to a global coordinate system. The global one, we're going to call it capital X, capital Y, and capital Z. We can also do this, right? So what does that mean? That means you can consider that this can be a vehicle. A vehicle is driving, or is running, and is moving with respect to a reference point, a stationary point. And this stationary point could be a building. Could be any reference point on the road. So if you want to know that if a car is actually spinning, what is the motion of this vehicle with respect to a point, maybe over there? So that's what we can study. And another type of problem by using Euler theory is, what if not only the car is spinning, what if the absolute or the global coordinate system is also moving? So this can be understood by establishing the connection between these 2 points. Because in any time, we can always define the position. If you set up a reference frame, you can also define the center of gravity of this object. And this object can be not necessary to be a plate, it can be anything, correct? So the main contribution for let's say the broader application for Euler theory is this. We can actually relate the rotation of an object locally, and let's simplify the problem, because the general motion or general rotation of this object doesn't have to be on the x or y or z, correct? It can be on any axis. However, suppose we simplify, we say that this is just going to be on y-axis. We're going to call it omega 2. And the omega 1 here, now let's not consider the rotation on the z-axis, but we're going to consider rotation on this z-axis. So this omega 1 is going to become this one here. And that's why the Euler theory can be more or very valuable here. Because rather than consider the two angular velocities within local coordinate system, you can move one of them from the local coordinate system to the global coordinate system. So what kind of problem becomes this? This becomes the problem that I just mentioned. What if we are actually spinning right here, right? And we are standing on what? On the surface of Earth. And we know that Earth is also spinning. So this way, you can actually determine that what if I have a spinning locally I'm spinning, but the coordinate system is also spinning. Then how can I calculate the absolute linear velocity and the absolute linear acceleration on the object by considering my reference frame is spinning?